It is my pleasure to introduce Massimiliano Berti from SISSA, Equivariant critical point theory and bifurcations of 3D gravity-capillary Stokes waves. Welcome.
So, thanks a lot again for the invitation. Already last week, I thanked you, and so thanks for coming again. Okay, so now today I wanted to discuss, in fact, related but different topics with respect to the previous week, and regarding, in fact, the existence and bifurcation of multiple gravity capillary Stokes waves. And today is the plan. After a short introduction and presenting the water waves equations, I will give, in fact, the main results and then the ideas of proof. Okay, so again, so the main actor are Stokes waves, which had been devised by Stokes in 19th century, and he constructed the existence of global in-time solutions, which are a rigid periodic profile, which travels with a certain speed c. The waves that he constructs are clearly 3D waves, but they have a strong symmetry. That is, they are actually constant in a direction. Actually, here they're constant along, we see all the direction orthogonal to the one of propagation. That is, we have here, we can say there are functions which are periodic in x, they travel with a certain speed, and which are constant in an orthogonal direction. So there are peculiar 3D Stokes waves, which are peculiar because they have an inherent symmetry that is of being constant in one direction. At the time, this actually was a controversial discovery, and the reason is that the possible existence of a wave packet u, which rigidly translates with a common speed c, is not that obvious. It is not obvious from the linear theory, because any plane wave, so if we consider an initial wave packet, which is composed by different plane waves, each plane wave travels with, like in this way here, and if the wave number j, according to the wave number j, it travels with a different speed. Then these speeds, omega j over j, may be different, and then, in fact, may lead to phenomena of dispersion, for which, no coherent structure like the Stokes waves may occur. And in fact, in any case, Stokes constructed the first approximate solutions of solutions of this kind here, and then the first rigorous complete proof was given much later by Levi-Civita and Nekrasov in the pure gravity case. Okay, since then, an enormous literature concerning these 2D Stokes waves have been given, local bifurcation results, also including capillarity and vorticity. Then, of course, they celebrated also results about global continuation of these branches of solutions. Also, the fact that there have been also given regularity results for this free boundary problem. If the free surface, for example, has a certain regularity, then actually it has to be analytic. And then let me quote also in the last, say, 10 years, we constructed also other very natural object that has quasi-periodic in time traveling Stokes waves, that is solutions like this, eta of tx, and then of course also the corresponding velocity potential, which are global in time, which are quasi-periodic in time, and which are more or less, which are close, which are approximations of, which are approximated by which are close to the sum of an arbitrary finite number of Stokes waves which travels with different speed, C1, C2, C2, and which have to satisfy some suitable non-resonance condition in order to exist. Okay, and then also the quasi-periodic Stokes waves. But today I would like to discuss, on the other hand, the issues about truly 3D Stokes waves, so Stokes waves which are Stokes waves which are not symmetric along some directions. The first existence results had been given in the case of gravity and the capillary in presence of surface tensions. And I will distinguish in two cases that now I call non-resonant and resonant. This terminology will enter into the subsequent part of my results. So the first results I had obtained in the case of non-resonance, which corresponds to the fact that when there are only two wave vectors in the Z2, which corresponds to a same possible speed of bifurcations. In the last week, in fact, Slim asked which are the possible speed of bifurcation. Of course, the possible speed of bifurcations are speeds which are present in the linear waves. And on the other hand, now I will discuss, and then the case in which the resonant case where there may be more, an arbitrary high number, always finitely many wave vectors. So more linear wave, more linear Stokes waves, which travels at the linear level, corresponding with the same resonance speed. So for which there might be several independent vectors, frequency vectors, which enter in resonance, giving rise to the same possible speed of translation of the Stokes waves. And in this resonant case, I will describe more in detail later. The more general results which had been given is given by Walter Craig and Nichols. Actually, I probably heard it when I was here at Field some years ago. And it, in fact, exploits the Hamiltonian structure of the water waves equations, as I will describe later. In the pure gravity case, let me mention that, in fact, also traveling truly three-dimensional Stokes waves were constructed by Jos Plotnikov. This is a small divisor problem, also at the level of traveling waves. The corresponding existence of quasi-periodic traveling 3D Stokes waves then has been actually obtained last year. And I finally mentioned that also for 3D waves, there is also an analog of regularity theory that is also results like Walter Craig and Mattei, which tells again, if the surface tension has a certain amount of regularity, then actually it has to be analytic. It is an elliptic regularity result for the free boundary. Okay, then today I would like to present a result obtained this year with Tommaso Barbieri, who is here, and with Marco Mazzucchelli, which probably is online, concerning new bifurcation results about 3D gravity-capillary Stokes waves. I give here a rough statement, and I will give later a more precise result. So the fact is the following, that so we have the 2D Stokes waves. Okay, so 2D Stokes waves which travels with a certain speed and which carries a certain momentum. So Stokes waves which are constant along a certain directions and a certain momentum. Okay, these Stokes waves never come alone. Actually, there is always finitely many, multiple clusters of other 3D Stokes waves which have exactly the same momentum of the 2D Stokes waves and which comes all together. So 2D Stokes waves never travel alone, but always come in a cluster of others, truly 3D Stokes waves having the same momentum. This is, I will precise later the results. So here we'll say, if I have in blue the pure 2D Stokes waves, constant along a certain direction, okay, actually, and each carries a certain momentum, actually nearby there are also some others in the green and in red, 3D Stokes waves, okay, which comes together. I will describe later the more precisely the result, but this was a first rough statement. Okay, and then concerning the proof, that I think it is as much important also as the result, it uses new topological arguments, which are very general, and okay, it will reduce after a Lyapunov-Schmidt decomposition, which is potentially singular, to recognize the number of critical points of a certain function on a topological space, which is invariant under certain group of symmetries. I will discuss it a bit later. Okay, so after this introduction, now I start a bit more precisely in giving the result. Okay, so these are the celebrated water waves equations that I had presented already last week. So we have concerned the evolution of a fluid, a time-dependent fluid. Its surface, it is described as the graph of certain functions, which evolves in time under the action of gravity, and actually also surface tensions at the free surface. So the fluid is the velocity field u, it is incompressible, and the divergence of u is equal to 0. Divergence of u is equal to 0, and the fluid now we consider to be in a irrotational regime. So the velocity field is the gradient of a scalar potential phi, which we call the velocity potential. So rotation of u is equal to 0, and this subspace is invariant under the dynamics. Okay, so the velocity field u, the velocity fields the region below the surface, eta. It is the velocity potential phi, it is in harmonic functions inside the fluid domain. Then there are, of course, the impermeability condition of the waterways at the bottom. The bottom cannot be passed through the water, and it is the third equation. And then there are two boundary conditions which determines the dynamics. The dynamics which are given by the first and the fourth equation. That okay, particles which starts from the free surface remain on it forever. Kinematic boundary condition that we heard also in the previous talk. And then the continuity of the pressure given inside the fluid by the Bernoulli theorem, which are the first two terms, is compensated by the gravity force at the free surface and the presence of capillary forces. Capillary forces, kappa is the surface tension, and the divergence of this term here, it is the mean curvature of the surface. Okay, so these are the evolution system. Okay, and then let us say about now boundary, the conditions in X. For me here, I will consider the case where I want to consider Stokes waves. So we consider waves which are periodic in X. The period, the X, the space variable, belongs to an arbitrary, flat torus with generators M1 and M2. Okay. This is an Hamiltonian system. The canonical Darboux variables are in fact the profile eta and the trace of the boundary of the velocity potential. Then the harmonic the velocity potential phi is recovered, has the unique harmonic functions, which satisfies the Dirichlet condition at the top, the Neumann boundary condition at the bottom, and in this case, the periodicity conditions given by this flat torus. And then this is an Hamiltonian system. The Hamiltonian is the total energy, the sum of the kinetic energy, potential energy, and the energy will come from the capillary forces, which is this. This is the area functional, the area of the surface. And this term here, it is actually the whole kinetic energy, and which can be reduced, as it was done by Walter Craig and Catherine Sulem, to just an integral on the free surface in quantities which happen here only at the free surface through in the introduction, in fact, of the Dirichlet Neumann operator, which is, sorry, is it here, which is in fact this operator here that taken psi the Dirichlet datum of the elliptic problems, which defines the harmonic function phi and gives the normal derivative at the free boundary. So that the problem is reduced only to the evolution of quantities which are given what happens only at the free surface, which is this one. And this is a system only eta, which is the free surface, the velocity potential at the free surface, which evolves in this way. It is a linear system, actually of quasi-linear set of differential equations, which is this one. It is an Hamiltonian system. It is quasi-linear, so a bit complicated, but it has some symmetries that, again, here will play an important role. So it is reversible. It is this is the reversibility. The Hamiltonian is left invariant by the action of this reflection operator rho. Then the system, it is all invariant under the group of the translations, which is a T2 torus group. This comes from the fact that the bottom is flat, and then the Hamiltonian is left invariant by this two-parameter group of translations, or the translation in all the possible directions theta. By another theorem, then there are then two conserved quantities, which are the two momentum, E1 and E2, corresponding to two independent directions, the translations along the axis, x1 and x2, which are these ones. And in fact, these are the Hamiltonian, whose Hamiltonian vector field generates the translations along the axis x1 and x2. Okay, and then overall, of course, the system is invariant under both these two, under both of these two groups, the translation one and the symmetry one. And then, in fact, okay, the Hamiltonian, and actually the Hamiltonian and also the momentum are indeed invariant under the group generated by translations and the reflections rho, which is this one. Okay, then now, okay, let us give now the mathematical formulation, more precise, concerning the 3D waves. So we look for rigid profiles eta breve, psi breve, which are periodic, which travels with a certain speed c1 and c2, which is unknown. Okay, so we insert these ansatz into the Hamiltonian equation that we obtained before, and then we have to solve this system here. That is, we have to find a speed c, c1, c2, and a profile u, periodic in x, which solves this system of equation. Okay. We already know that the solutions must be analytic here by the regularity results. Here we implement look for them into a space of analytic functions which are periodic in x, okay, which can be any functions periodic in x, any function periodic in x according to the period given by the lattice gamma. It is can be expanded in Fourier series in this way, and the corresponding momenta, the Fourier corresponding variable j, belongs so to the dual lattice j prime. Okay, so we have to look for these zeros of this nonlinear operator here. Then we remind that actually our problem is Hamiltonian. That is, so this operator, it has this Hamiltonian form. And actually CDX, I mentioned before, the generator of the translations is actually the Hamiltonian vector field generated by the momentum. So CDX is actually equal to the Hamiltonian vector field generated by the linear combination C dot I of the momentum. And so since J is a non-degenerate, we have only actually to find the critical points of this Hamiltonian here for certain values of the speed. So we have this functional here. And let me mention one, symmetry. I mentioned that the Hamiltonian and the momentum are invariant under the group generated by the translations and the reflections. And then actually, if I have a Stokes waves, then all its translated and all the reflected will be Stokes waves as well. Then they are not geometrically distinct, and so we shall say that the two Stokes waves are geometrically distinct if actually are not obtained by one another by translations and possible reflections. Okay, so we look for Stokes waves. This can be either two-dimensional, either truly three-dimensional. That is, it can be two-dimensional if they are already, if they are constant along a certain wave vector. A Stokes waves is 2D along a certain direction if it actually is constant in the direction orthogonal to this wave vector here. And otherwise, if the waves has no has no privileged directions in which along which it is constant, then we say that it is truly 3D. So truly 3D waves is solutions which has no symmetries, for which the symmetries are almost all broken, and of course can be also characterized so by knowing the set of the stabilizer. This is the set of translation parameters, T1 and T2, which fixes U. In the case of 2D waves, this is larger, it will be a straight line, whereas, or a one-dimensional subarea of the torus, whereas for the 3D waves, this, so a wave is truly 3D if have been broken all the symmetries, and then only the points theta which fixes U are only finitely many. Okay, so we look for small amplitude solutions. So we proceed, of course, it is by bifurcation analysis. So we look at the linearized operator at the flat ocean. It is equal to 0. So we have this linear operator, and we have to look at which has solutions which are small, close to C0. So the possible emergence of non-zero Stokes waves can only occur when C is we call the resonance speed. That is when when this the linearized operator at C is not invertible. This is the other resonance speed, and one can diagonalize this operator and actually realize that all the possible speeds of bifurcation C belong in fact to this web here. This web is the union of all the straight lines Rj, are resonant straight lines, which are all for any wave vector J are this the straight line that here I have written here. So Rj are given a certain vector J. Rj is the set of speeds C in the plane R2, which satisfy this. So they are a line which is orthogonal to J and which is at the distance from the origin, precisely given by omega J divided by modulus of J. This is the absolute value of the speed of a plane wave of vector J. So this web is the possible web from which Stokes waves may occur. Non-zero Stokes waves may occur. In other more physical terms, in fact, if we have that necessarily, so the Stokes waves can emerge only from a small displacement of the linear waves. So these are all the possible linear waves, mathematical, so it's the kernel of this previous operator here, which, and these are the linear waves which corresponds to the same common bifurcation speed, C star. Okay, that is, we take a certain speed C in the web, then there will be a non-zero kernel, which is given by this direct sum of planes, Bj, which are these waves. Each of these is formed by linear plane waves, which have the speed which corresponds to the same resonance speed C star. They enter in resonance among among them. So there is this huge, well, huge or not huge kernel of linear waves which are traveling with speed C star. From here may bifurcate some non-linear Stokes waves with the speed C nearby, close to C star. I also mentioned that all the linear waves which stays on this subspace have a certain momentum. The momentum is this vector value, is vector here. The momentum I computed on these linear waves with wave vector J, actually it has this form here. So it is this linear combination of vectors J with amplitude alpha J squared plus beta J squared. Okay. So these are the possible bifurcation regions. And in fact, I revisit in this way the bifurcation results that have been constructed so far. The first case is the first non-degenerate case. That is when the kernel of L star is the smallest possible. There exists only one vector J in nu. So this I call the resonant wave vectors. So there is only one resonant wave vectors. So there are no interactions among other linear Stokes waves. So in the case in which there is only one non-resonant wave vector corresponding to that, so the dimension 2, then we are precisely in the Stokes situation, which can be solved now from Krander-Rabinowitz theorem from simple eigenvalue. Why simple eigenvalue? Because I said that here the dimension is 2, okay? But nevertheless, since the symmetry has these rotation and translation properties, actually one can reduce with no loss of generality to study the problem from only one-dimensional kernel. The other situation which occurs in dimension 2 is when there are two independent wave vectors parallel one each other, like here I wrote, for which the two linear waves enter in resonance among them, actually for which the speeds of translations are the same. This is the case known as the Wilton-Ripple cases. In this case, so we have 2D, we could expect a bifurcation of 2D Stokes waves in a resonance setting. Okay, and in fact, some results I've obtained since last century. Here, from a bifurcation point of view, the situation is that we have, so something has to be done because the speed is only here for two-dimensional case is only one scalar unknown, but the kernel is high dimension, so I cannot only solve the problem moving and finding the speeds in terms of the linear waves. And in fact, we have recently obtained, using variational methods, very general results concerning the existence of these waves. And this is here in the picture. It is precisely the fact that for 2D waves, this is the Wilton-Ripple case. So here it is the plot of the functions omega j over j, according to the different values of gravity and capillarity. They have these shapes here. So if there is, so the number of solutions of this equation is at most 2. So there can be only 2 waves, which in the plane may give rise to the possible to cooperate in order to make traveling waves with 2 independent speeds, which are the Wilton-Ripples. For waves which are truly three-dimensional, the situation is more complicated. So then one looks at the other case in which the dimension of the kernel is 4, but when the vectors J1 and J2, J and J star are not parallel one each other. So if they are independent vectors, I call these the non-resonant bifurcation results of 3D Stokes waves. And here we are in a situation which is parallel to the one of the Krander-Rabinowitz bifurcation theorem, because now we have 2 parameters to move, because C1 and C2, and the kernel is 2-dimensional. Again, here, the kernel here, I wrote it to be 4-dimensional, but because of symmetry induced by translations and reflections, actually one can reduce with no loss of generality to a 2-dimensional kernel. And so also here one can formulate this as a bifurcation theorem from a double eigenvalues, but with a number of parameters 2 exactly has the dimension of the kernel. And so it is an analog of Krander-Rabinowitz theorem. Whereas the situation that I wanted to discuss now is in fact the last one, that I call the resonant case. Then when the kernel is it has a higher dimensions. So there are many Stokes waves, all these ones, which carries the same linear split C star. And okay, we have only, of course, two parameter speed, C1 and C2. So again, we have to do something because there is a higher dimensional kernel with only two parameters, speed C1 and C2. And in the case, so the linear theory, so there are at the linear level a huge kernel of waves, which corresponds to the same speed C star. Among these, they can be either there is a coexistence of either 2D and 3D waves, because of course, if there are 2D waves, if all the amplitudes alpha j and beta j are all zeros except for only a vector j, then these are, of course, is a plane of waves which are only two-dimensional, because are those which lives on a specific wave vector j. If on the other hand there are if on the other hand there are two wave vectors that I call here j and j prime, not parallel, for which the amplitude alpha j and beta j are non-zero, then these waves have broken all the possible symmetries, so these waves are really three-dimensional. Okay, so this is the situation, and then now I formulate again more precisely the question that I had posed at the beginning. So we are in a resonant case. Then we consider certainly there exist 2D waves, because there are certainly 2D waves applying the 2D theory. So the 2D Stokes waves, they carry a certain momentum, and then I call it A. The momentum of the wave is, for a 2D wave, is necessarily parallel to its wave vector. That I remember is given because of here. So if I have a 2D wave, all the amplitudes are zero except only for one j. So I eliminated the sum here. So its momentum is proportional actually to this wave vector. And then we ask whether, so the natural question is the one that I posed at the beginning. So if there are other 3D Stokes waves with the same momentum, which appears and travels simultaneously with these 2D Stokes waves. Okay, and then actually this is what actually happens, and here I give, in fact, so the result more precisely. Okay, so I said that, so we consider the case in which, so there are the wave vectors, I call it here, say, for example, J1, J2, and Jn. In the picture, I've written J1, J2, and J3, and then we consider the cone, which is the one generated by J1, J2, and J3, the opposite direction, simply because minus J1, minus J2, minus J3. So this is 0. We consider the blue, the resonant cone, this is C. These are all the possible values of the linear momenta. Let us recall here. The momentum I of all the linear waves is a linear combinations of certain scalars times j. So all the linear momenta of the momentum of all the linear Stokes waves belongs to this cone here. Well, then, okay. Then we consider, okay, we have, we take, for example, in this picture here, we consider a specific wave vector, which is in the interior of the cone. I will say after what happens if we take a wave vector not in the interior. That is in this picture if we take this or this. So we take a wave vector in the interior. Here I call it J0. And okay, then we know that there are Stokes waves which are 2D Stokes waves which are generated on J1, so which are orthogonal to the direction of for example, here, okay, let me call this J0. So Stokes waves which are orthogonal to the wave vector J0. Okay, actually, okay, so this is, they have a certain momentum A. So for any value of the momentum A, which is here, sufficiently small. So for any value of the momentum A, sufficiently small because I'm doing a bifurcation results, then there exists a certain number of other geometrically distinct truly 3D analytical waves which have the same momentum, and they have the following form. They are, in fact, the deformation, a nonlinear deformation of suitable Stokes waves, V1, V2, Vn, which will be selected, which are selected indeed by the nonlinearity. And they have a certain speed, c, which is close to the unperturbed c star by these quantities here. Let us see that, so this inequality is consistent because the cardinality, the number of resonant wave vectors in this case is at least greater or equal than 3. Otherwise, we are not in a resonant case. And then actually this provides that there exists at least one truly 3D Stokes waves which carries the same momentum of a 2D Stokes waves. Okay, the key difficulty, in fact, is improving, well, there are several, but one key difficulty is improving that we shall prove that these waves are really 2D because these VI, so the linear waves, are truly 3D linear waves, and then this will be perturbation of two truly 3D linear waves. These are difficult because we shall find these solutions VI has critical points of a certain function, and then we have to know that they will belong to the subspace of truly 3D waves, which is okay. So we want to prove that actually the VI have a really at least two independent active frequencies for which, so there are really three dimensional. We have broken all the possible symmetries, which does not happen, of course, for the Stokes waves which lives on J0, which is this one, which is in fact constant in the direction orthogonal to J0. Okay, so this is actually the completely novel case which had not been investigated before. What happens for the momentum A, which is collinear to one of the unperturbed linear vectors? The result by Walter, Craig, and Nichols. I have considered the case in which the momentum A is independent, is, say, here. So the case where A is not collinear to none of the linear wave, resonant wave vectors. In this case, we improve the results, okay, by Craig and Nichols. Okay, in two ways, if A is not collinear to any of the resonant wave vectors, we find this number n, which is given by this, so the number of resonant wave vectors minus 1, truly independent analytic Stokes waves, geometrically distinct, and this result improves the one by Craig and Nichols in two ways. One, because the number of solutions that we find is the doubles as what they find. In fact, they had neglected the Z2 symmetry, so actually we are able to distinguish also these ones, and also because for a reason that will be apparent from the Lyapunov-Schmidt decomposition that we shall do, they need, if A is closer and closer in the construction of Craig and Nichols, if A is closer and closer to one of the resonant wave vectors, they have to take the amplitude, the momentum, and so the amplitude of Stokes waves is smaller and smaller. Because, okay, on the other hand, we are able to take only an A, which is small but uniform, and we can approach also to the resonant Stokes waves. And the reason for which we can improve this is to exploiting along the Lyapunov-Schmidt decomposition to really exploit the symmetries which are given by the 2D wave. 10 minutes, sure.
questions.
Yes, okay, I will go. Then the third result, we can call it, say, rigidity results, which tells what happens. So any sufficiently small Stokes waves with the speed sufficiently close to C star, it has a momentum, A. Actually, A has to belong to this resonant cone. So A has to belong here. And furthermore, if A actually is on the boundary, so which is the case that I discussed here, so if A is actually parallel to one of the extremal resonant wave vectors of the cone, actually the solution is necessarily 2D. If A, on the other hand, is the interior and is not in one of the resonant wave vectors, necessarily the solution U is 3D. So this also complements the PV results in the sense that the fact that the existence of the Stokes waves with the momentum A, which is in the cone, it is a necessary conditions. Outside there are not. And if I wanted truly 3D waves, it is necessary that A has to be taken into the interior of this cone here. Okay, then a few sketch of proofs. As I said, we are going to use a variational argument after Lyapunov-Schmidt decomposition. The major steps are the construction of the speed C in a whole neighborhood of the kernel V. Then we shall have to understand the topology of the sets where the momentum is constant, and then, okay, some other thing. Very few things. So start as usual Lyapunov-Schmidt. The equations may be decomposed into two equations along the kernel V and its supplementary subspace, here the symplectic orthogonal. And then by one solves the implicit function theorem and the range equation, plugging into the bifurcation equation, and the bifurcation equation, which is this one, actually it is again the Euler-Lagrange equations of a problem, which is inherited by the variational structure of the original problem. And in fact, there are nothing else but the critical points of the Hamiltonian restricted on this manifold, which has inherited all the symmetries of the problem. In particular, also it contains the fact that the critical points are restricted only on the two-dimensional planes, where all the vectors are parallel to a certain vector J, actually are true critical points, and then this is the existence of the 2D waves. Okay, so first thing, the speed C. The speed C we impose in order for this following Craig-Nichols in order to solve this equation here. So that, well, actually a small variation of what I did, but it is that, in order to solve this equation here. We have two equations, two unknowns. What the difficulty with respect to what was done by Craig and Nichols is precisely that we must approach also to the resonant cones. Actually, we shall look for also what happens here. And the difficulty is that because when one goes to solve this equation, by the implicit function theorem argument, its linearization close to these planes here becomes singular. Nevertheless, exploiting the fact that there are really these symmetry inherited by the two-dimensional subspace, one can nevertheless show that there is compensations among these. The singular effects are compensated by the symmetries which come from the 2D, and the outcome is that one is able to construct the C of a V in a full neighborhood of the, so in a full neighborhood, there will be the bidimensional planes, Vj. We are able to construct C of a V in a full neighborhood. Okay, then the heuristic principle would like to take the constraint, the momentum restricted to this natural constraint, and to look for critical points of the Hamiltonian on this restricted manifold. The problem is that in general, this is not a manifold, and we have to understand actually what is the topology of these level sets. The best way is done as follows. Since this is a purely quadratic part, the restricted momentum is a perturbation, cubic perturbation of this quadratic part produced by the Lyapunov-Schmidt decompositions. Then we want to rectify this perturbed momentum, showing that actually after a suitable change of variables, after a diffeomorphism, then actually we are able to recover the purely quadratic vector-valued momentum I. And this can be done. Again, there are the proper problems induced by the symmetries here. But okay, using here the singular, one can solve. Finally, then one obtains, we can study how it is done, the topology of these sets. A first result in this direction is that the set where the momentum is constant, which is this one. Actually, of course, it is the disjoint, on what happens of the planes generated by the 2D waves and what happens outside them. It turns out that, we have the 3D waves and then the portion on the 2D waves when A is parallel to the momentum J0 are only the 2 waves along these directions. Here there is a manifold, and we have this direct sum decomposition of the space. And so this will give the natural constraint. The critical point restricted on this momentum fixed will be a true solution as well. Okay, I go faster. So with this, I will conclude. And then at this point, we shall have a space, which is a compact, which is the level set, a strange space, the topological space, which is the level set of this momentum, which is composed by 3D waves, and then disjoint to union with a unique 2D waves, say here, which is where here the space is no more a manifold, outside yes. Okay, on a compact topological space, a function has a maximum and a minimum, for sure. So the 2D waves, it is all at a certain level. So maximum and the minimum. So either the maximum is equal to the minimum, and then the function, of course, is constant. So we have found a continuum of Stokes waves, or at least there exists, or the maximum or the minimum is different from the level of the unique Stokes waves. And then here, certainly, we have constructed the existence of other 3D Stokes waves. This is the finish for the existence. For the multiplicity, that one has to exploit only the more complicated geometry, so the rich topology of the space. And so I finished here.
You have to turn it off while he speaks, otherwise it's make noise. But as soon as somebody, you take this off. Okay. And you open it. So now, when you present, you can open it.
Okay. So that the people online can hear it as well.
And you don't have to be too strict.
No, I won't. 15 minutes.
Oh, by the way, I agreed to chair at tomorrow's session on the condition that if